For those of you who don't know, what I was showing before was the Einstein at Home screensaver, and I'll say a bit more about it during this talk. I encourage you to go to their website and sign up. It's actually doing real analysis for LIGO and GEO, looking for signals from pulsars. So I'm giving this talk on behalf of the LIGO Scientific Collaboration, and as many of you know, there's 4 main working groups in the collaboration looking for astrophysical signals. There's the burst working group, the inspiral group, and the stochastic background groups, and also the periodic group. And I'll be talking mostly about those sources. Here's an image you've probably seen of the Crab pulsar, and that's one of the top candidates for periodic sources from known pulsars. And also important sources would be LMXBs, for example, or maybe unknown neutron stars that are nearby. So I'll begin just to give a quick status by giving a quick status of the LIGO interferometers now. I'll give an overview of the different periodic searches we're doing with LIGO and GEO. And then I'll mention the nature of these signals, what they look like, and I'll describe in detail the time domain Bayesian search method, which is a targeted search method which we're using for radio pulsars. And I'll show applications of this method to data from S1 to S5, which from data that was just collected in the past month, mainly on hardware injections for S5. I'll mention a bit more about the other searches that are going on in the periodic group and our future plans. So since its inauguration in '99, LIGO has had 4 science runs that have completed, and we've carried out analysis for signals, astrophysical signals. And the S5 science run just started about a month ago. And in each science run, the sensitivity of the interferometers has increased significantly. And now we're close to design sensitivity, or we are at design sensitivity for S5. So this is a graph of the sensitivity of LIGO about 2 months ago, before S5 started. The yellow curve represents the target we had set for LIGO, and as you can see, for the 4-kilometer interferometers, you can see over a broad frequency range, the 4Ks are at design sensitivity now. And this is a figure of merit we use in the control room from just 2 days ago on Sunday. And you can see that the green line here represents the sensitivity of the Livingston interferometer to binary neutron star in spirals. And we're sensitive to up about 10 megaparsecs for L1 on Sunday, about 11 for H1, the 4-kilometer in Hanford, and about 5 megaparsecs for H2. And so far in S5, we've accumulated approximately 260 hours of triple coincidence data between the 3 interferometers. So in the periodic search group, we've got 2 main classes of searches, the coherent searches and the incoherent searches. In the coherent searches, there's this time domain method I mentioned, which is for targeted sources like radio pulsars, for example. And initially in S1 and S2, we only had code to look for isolated pulsars, but now we've got also the ability to look for signals for pulsars in binary systems, and we're doing that for the S3 and S4 data. And we've also got an extension of this using Markov chain Monte Carlo methods, which permits us to extend the parameter space slightly over a narrow frequency range, not exactly at the frequency of the rotation of the pulsar, or twice the rotation of the pulsar, as we usually do, so we can have more templates. And these are finely tuned searches over very narrow parameter space. I'll talk a lot more about those. Then we also have an F-statistic frequency domain method. The F-statistic is an optimal filter used to look for signals from pulsars. And with this method, we've conducted an isolated all-sky search over a wide frequency range on the S2 data. And this is also the same method that the Einstein at Home project is using. And also, we're using this method to look for signals from SCOX1 now, but we'll be expanding this to other LMXBs in S4 data. So these are good for deep searches over broad parameter space over a wide frequency range. And then finally, the incoherent searches, the Huff transform, the stack slide method, and also power flux. These are very efficient, robust, wide parameter space searches where we can search over the whole data rather quickly and efficiently, whereas for coherent searches, they're much too computationally limited to look at long stretches of data. So for example, for S2, we were only able to use 10 hours of data for the F-statistic method, whereas for the incoherent searches, we were able to use the whole data set. So far, the Pulsar group has about 5 main results based on these searches. The first one, in S1, we set upper limits on gravitational waves from Pulsar J1939 plus 2134. We picked this pulsar mainly because it's the fastest rotating pulsar, and it gave us the most interesting upper limit on the ellipticity, but also when we started applying these methods to the data, the detectors were much more sensitive at higher frequencies. And in this paper, that's where we introduced both time domain method and also applying data to the F-statistic method. Then in S2, we had a PRL paper setting upper limits on 28 known radio pulsars. And in this paper, we were able to do a coherent search. So we're able to use the data coherently from all the detectors to place limits on these pulsars. I'll talk a lot about the results from this paper. Lately, just this past month, the paper has appeared in PRD where with the first all-sky upper limits from LIGO using the Huff transform over a wide frequency band. There's a paper which is in the final phases of reviewing the LSC for coherent searches over a wide frequency band, and also putting limits on waves from SCO-X1. And also, you can find some results from Einstein at home at this website using S3 data. And S4 data is currently being analyzed. So neutron stars are good potential sources of gravitational waves. First of all, they're known to exist. And in some cases, we can observe them electromagnetically, and that reduces the parameter space a lot, which means we can set tighter limits because there's less chances of false alarms. So there are several mechanisms that could lead neutron stars to emit gravitational waves. The one we're most interested in for the targeted searches are bumpy neutron stars, triaxial stars that would emit gravitational waves at twice the frequency. But it's also possible that young neutron stars could emit gravitational waves due to R modes. And if neutron stars are precessing, we could see a signal at the rotation frequency of the pulsars. And of course, low mass X-ray binaries are the most interesting sources because there's a clear mechanism for causing the asymmetry in the neutron stars with the accretion. But it's a very difficult problem due to the fact that we have to also search over the orbital parameters, and so the parameter space to explore is really large. So computationally, it's very difficult. So we define the gravitational wave amplitude as this, where epsilon here is the equatorial ellipticity, and this is the maximum strain we could measure for an optimally oriented neutron star. So it's proportional to F naught squared, where F naught is the frequency of the pulsar. So most of the pulsars we're looking at are high frequencies. And epsilon here is a measure of the asymmetry of the neutron star. And so we can, by setting up limits on the gravitational wave amplitude, we can also put limits on the equatorial ellipticity, assuming this model. And the figure here is quite exaggerated, but the limits that we're placing now for the ellipticity of neutron star are of the order of 10 to the minus 5, 10 to the minus 6. So the signal produced from such a triaxial neutron star can be modeled as this. The emission will be at twice the rotation frequency of the pulsar, which is 5t here. The F plus and F cross are the antenna patterns of the interferometers, which depend on time as the Earth rotates, and the polarization angle of the signal, the amplitude, and cos iota. Iota is the inclination angle of the neutron star with regard to the line of sight. So in targeted searches, we only look at twice the frequency of the pulsar, but for blind search, and these are the unknown parameters in in the signal, the amplitude, polarization angle, inclination angle, and the initial phase of the pulsar. For blind searchers, we also have the frequency of the pulsar, the spin down of the pulsar, the frequency derivatives, and also the location are unknown. So for the radio pulsars, we can predict the phase extremely well from radio observations, and we're collaborating with scientists at Jodrell Bank Laboratory, Observatory, so they can actually measure the phase of the pulsars for each science run. And so for each pulsar at the Solar System Barycenter, in an inertial reference frame, the phase can be modeled as this. So we have to correct the data that we get at the timing of the data we get at the detector by a phase shift, a time delay to put it in the Solar System Barycenter, and this consists of the Romer delay, relativistic delays, and in the case of a binary pulsar, we also have to take into account the time delays that are due to the orbit of the pulsar. So the largest of these is just the Romer delay, which is given by this equation here, where r is just the distance vector from the Solar System Barycenter to the detector, and k is a unit vector pointing in the direction of the pulsar. The second order term here is only relevant, it's parallax, and it's only relevant for nearby sources, so it doesn't actually apply for any of our sources that we're looking at. We've checked our timing software that we use in the LSC to make sure that it agreed with the radio astronomy packages, and the timing residuals between our software and theirs is less than 5 microseconds. And for most pulsars, timing noise, which is seen, is not important for us, but except for the Crab pulsar. And the Crab pulsar, the timing noise, if it's tied to the rotation of the pulsar, is large enough that it could prevent us to see a signal. So we actually correct for that. But for other pulsars, like this is example of timing noise for B1937 plus 21, and this is over several years, and the timing residuals are only of the order of a couple of microseconds. So what we do for radio pulsars is we begin by heterodyning the data of coming out of the detector by e to the minus 5t, where 5t is the phase of the pulsar offset by just the initial phase. So if you take, this is the data coming out of the detector's signal plus the noise, you multiply it by e to the minus I5t, and we low pass filter it, and then we resample the data so that what we have left is just this part of the signal, which only varies very slowly to reflect the beam pattern of the antenna, and the noise for each of our bins, or B's of k bins. So this, for example, is a plot of the B's of k's for a hardware injection that was injected in H1 data recently. So the red dots represent the imaginary part of this signal, and the black dots, the real part of the signal. So this is for a pulsar with a signal with an amplitude of 10 to the minus 22 that was injected in H1. And as you can see, this is over the course of 9 days, and we can clearly see a signal there. So, and then once we have the reduced data set, these B's of k's, we just take a Bayesian approach to determine the joint posterior probability of each of the unknown parameters. So this is just Bayes' theorem. So we just want to determine this. We need priors, and we just use uniform priors for all of the parameters. For H0, now that we've been able to set upper limits from past science runs, now we can start using a prior which reflects what we've learned on in previous runs. The priors we're using are the least informative ones. So we could, if we were basing our priors on physics and using arguments like the Spindown arguments for the setting upper limits on the gravitational wave amplitude from pulsars, then basically we wouldn't get any new information in our posterior, because our posterior would just reflect our priors, because our priors would be too tight. So the reason we're setting flat priors is just so that we can see what we're learning from the experiment. And of course, if we were to see a detection, then we would have to apply a reasonable prior to really, before we could claim a detection. The likelihood comes in here, and I'll explain what we use for the likelihood function, and then just normalization. So in the S1 paper, we started, for the likelihood, we just used a bivariate normal distribution. It's bivariate because the B's of K's are complex. And we determined the sigma k, the error associated with each B's of K, by using a 4 Hertz band around the frequency of the signal. But we ran into some problems doing this because, for example, in this pulsar in S2, there's a huge spectral disturbance right next to the frequency of the pulsar. So this was throwing off our estimates of the error. And this became important in S2. So what we did is we just marginalized over the sigma k's here to get this likelihood, which is just a student t distribution. This is what happened in S1, actually, when we were looking for signals from B1937 plus 21. And the signal frequency for it was at 1284 hertz. And unfortunately, this is over 18 days for the S1 run. And the signal we were looking for was exactly just about at 1284 hertz. So if we had been estimating the noise just in a, for example, 0.1 hertz frequency range, it would not have been such of a problem because at least we would have correctly estimated the noise. But since we were estimating the noise over the whole range, this meant that we were essentially underestimating the noise. And so this gave us some problems for the results from the geodetector in this one. So to set upper limits, we just marginalize over the nuisance parameters, the orientation of the pulsar, for example, in the initial phase, so that the only parameter we're interested in is h0, so that we get the posterior distribution for h0. And then we define the 95% upper limit by the value that bounds to 95% of the cumulative probability of h0. So just to summarize, an overview of the method is we take the raw data, we heterodyne it at the correct phase, and low pass, average, and calibrate the B's of K's. So for this method, we're just looking at one frequency bin where we expect the signal to be. So it's not a broad band search at all. And then we downsample to a 60th of a hertz because once we've heterodyned the data, the only time varying component of the signal is the beam pattern of the antenna, which only varies over the course of a day. So by downsampling to once per minute, we still have large enough bandwidth to cover the signal without loss of information. Then we compute the joint likelihood for the data given the signal. We put in the model, which is posted here, and then we can compute the posterior PDFs. And then by putting in uniform priors, then we can compute the upper limits on the strain. So one of the nice things about this method is that it's trivial to expand this to do a coherent search using data from several interferometers. So the combined posterior just comes out by multiplying by the product rule, and you just multiply the likelihoods from the different detectors. So even if the detectors aren't all online at the same time, for example, it doesn't matter. You can still do a coherent analysis. And this is an example of, on simulated data, if you had 4 detectors, for example, the dotted line showed the upper limits you could get from each of the 4 detectors if you have similar noise in the data from similar sensitivity in all 4 of them. And then the solid line represents the joint posterior that you would get. And it's roughly a factor of 2, square root of 4, that an improvement that you would get in sensitivity. This is another example on simulated data. And in this case, again, the solid lines here represent the posteriors you would get. So this is for the gravitational wave amplitude, the marginalized posteriors for the amplitude, the marginalized posterior for the phase. This is for the polarization angle, and this is for cos iota. And in this case, if you were just taking data from one detector, you would have a very weak detection, very low signal to noise. And you can see that if you include the data from all the 4 detectors, then the posterior peaks a lot more sharply. So the cos iota, the orientation of the pulsar, and the amplitude of the signal are strongly correlated when the cos iota is not equal to 0. And so even under conditions of high signal to noise, the posterior for H naught can be widened due to this covariance. So this is just an example, and also the polarization angle and the phase are also highly anticorrelated. So this is an example of an injected signal at 0 and 180 degrees, and you can see the equal probability lines in this joint posterior. And the same here for cos iota and H naught. So what this gives rise to is that even when there's no signal in the data, because of the priors we're using for H naught, you get that the joint posterior between cos iota and H naught peaks at cos iota is equal to 0. So this means that when there's no signal, this is interpreted as a pulsar having an unfavorable orientation. So when I'll show you some of the results we've had in the previous science runs, if you just look at the posterior for cos iota, it peaks at 0. And this just means that it, given the prior we're looking, it's suggesting to us that if there's a pulsar signal there, it's not favorably oriented. So using simulations, we can calculate the expected sensitivity of the search. So using, in this case, using like 4,000 sources randomly distributed in the sky, you can calculate the average upper limit that you would get, which given a certain power spectral density and a certain observation time. So the upper limits that we'd be able to set are inversely proportional to the square root of time. So as we gather more data, our sensitivity, signal to noise, will increase as square root of time. So the width of this distribution is actually quite wide. So this is the histogram of the upper limits that you get using data, using all the same noise, which means that even given data from the same sensitivity, you can easily have factors of 2 of difference in the upper limits that we set.
Why do you think that is?
It might be due to the marginalization over the orientation and the correlation between.
The noise, but it's the distribution of the nuisance parameters
Yeah.
for the actual
Yeah.
source as well as anything.
That makes sense.
And so using this number of 10.8, we can calculate the expected sensitivity of the data given a certain observation time and power spectral density. So for example, using post S4 sensitivity curve for H1 that was in August, end of August this year, and if you assume that we had data for a year, this curve, the blue curve, represents how sensitive we would be to pulsars, and the dot here represents the crab pulsar. So the black dots here represent the spin-down upper limits for each of these radio pulsars. So this is, if you assume that all of the rotational energy lost, because some of these pulsars are spinning down, and if you assume that all that rotational energy loss went to gravitational waves, these would be the upper limits on gravitational wave emission. Now, many of the pulsars that we're actually searching for don't appear on this plot, because many of them are in globular clusters, and they're actually, to us, it appears that they're spinning up, because they're being accelerated in the globular clusters, and we don't actually have a handle how to measure their intrinsic spin down. So this is a bit of a hand-wavy argument to make, because for some of the pulsars, they're actually spinning up. But for the crab pulsar, it's the one that's spinning down the fastest, that's in our frequency range. And you can see that with 1 year of data at current sensitivity, we would be able to constrain its gravitational wave emission better than this spin-down model.
That 60 Hz line is not relevant.
It's not, and I'll show a plot showing that later. But if you actually do an FFT right next to the 60 Hz line, the crab emission frequency is around 59.6, and it's far enough away from the 60 Hz line that it should not be affecting our results. Now it may be, but that's something we should be able to fix, but just by using tighter filters. But
It'd be nice to fix the 60 Hz line.
it would be nice to fix the 60 Hz line too.
S5 data would we need before we start to see this? If it's out the number?
Well, so this is using roughly S5 sensitivity using 1 year's worth of data.
can't see what the difference between the curve is, but at what square root of t does the black dot correspond to the delta limit line? Is it 1 month of data?
Well, you could say 6 months, but the thing is also I was showing that there's a wide, the distribution is quite wide, so given one 6-month stretch, you could have an upper limit which is a factor of 2 larger or bigger. So it's going to be order of a year. And the red line here represents the sensitivity we'll have with 1 year of data at advanced LIGO sensitivity. And the black lines cutting across here show our sensitivity to neutron stars at a distance of 1 kiloparsec with ellipticities of 10 to the minus 6, 10 to the minus 7, 10 to the minus 8.
What fraction of all these known pulsars were discovered in the last 5 or 10? Well, how many more do you expect to have by the time advanced LIGO comes?
Right. So actually, this plot is somewhat dated, and there's been at least 500 pulsars probably discovered since this plot was generated from the Parkes multibeam survey. But the majority of them are at much lower frequencies. And actually, I think the Parkes multibeam survey was mostly geared, it was not geared towards high frequency pulsars. So there are some new ones, but also some of them are spinning up, so they don't appear in the plot anyway. But right now there's around 150 pulsars that have spin frequency, twice their spin frequencies above 50 hertz. And we could expect that number to grow significantly between now and advanced LIGO, I think. So some of the results we've had so far with this targeted search. S1, we set an upper limit on B1937 plus 21 using both LIGO and GEO data. And the best upper limit came from Livingston, and it was 1.4 times 10 to the minus 22. And then in the S2 science run, we set upper limits, they're not preliminary anymore, for 28 known isolated pulsars. And we also did our first end-to-end validation of the analysis method and also the timing between the sites using hardware injections in the interferometers. And we included the crab pulsar, and we were using an extra heterodyne for it to account for the timing noise. In S3 and S4, we did some additional hardware injections in both GEO and LIGO. And for the first time, we were able to check that the timing was consistent between GEO and LIGO. After S3, we did this. We added binary pulsars to the search. The reason we only had 28 pulsars in S2 was because most of them are, many of the pulsars above 50 hertz are in binary systems. So we were able to expand our set of pulsars quite a bit in S3. Given the new timing check between LIGO and GEO, we did the first coherent analysis between the two sites. And we're within an order of magnitude from the spin-down limit of the crab. And in S5, we plan on well, we've already checked that the hardware injections seem to be successful. We're planning to expand the number of pulsars to include new discoveries. And there are some other old pulsars which we've not included in previous analyses because we didn't know the source parameters well enough to conduct this one template search for them. And we plan to perhaps extend the analysis to also look for signals at other frequencies. We could look at the pulsar frequency, for example, or maybe 4/3 the frequency where R mode signals would be. And then we need to increase the efficiency of the code as well. So in the S2 analysis, we analyzed 28 pulsars with the gravitational wave frequency above 40 hertz. For 18 of them, the timing was provided by Jodrell Bank Observatory. 10 of them, we used the data in the ATNF catalog. And there was an additional 10 pulsars above 40 hertz, but we didn't know the spin parameters well enough to include them. We limited the analysis to contiguous 30-minute segments of data, but that covered about 88% of the S2 data. And in total, we had 910 hours of data from H1, 691 from H2, and 342 for L1, and these are the duty cycles. And these duty cycles are a bit worse than perhaps what you've seen from other searches because we have different data cuts when we implement this search. And these were the first direct upper limits for 26 of 28 of these radio pulsars. This plot is just to show that there's no highly preferential direction in the sky for this analysis in terms of sensitivity. So the red curve here shows the average antenna pattern for LLO, or Livingston Observatory, over the course of a day. And then the black, over the course of S2, in fact. And then the black one shows the average antenna pattern for the Hanford interferometers. And the histogram here represents, this is in declination in the sky, and the histogram represents the number of pulsars we have at minus 80 degrees in declination, minus 30 degrees, and so on. And you can see that just due to the antenna pattern, you wouldn't expect the difference in upper limits to change by more than 30% or 20% or so. So in the S2 hardware injections, well, we injected two signals, one at constant frequency and another one which was spinning down. Here I'm showing the extracted parameters for the signal at constant frequency, P1. The position parameters are here, and it had a phase of 0 and so on. It was injected at a frequency of 1279 hertz. And as you can see, the red line here is L1, green line L2, H2, and the blue line H2. H1 and H2, and then the black line represents the joint analysis between all the interferometers. So just like it worked in the simulations, it works well on the data, and this was a good, increased our confidence that the timing was good between the sites and that we could do a coherent analysis.
These four dimensions are highly correlated, right? And so when we see, for example, a black curve that for psi that doesn't really agree with the prediction with the
right.
That's probably okay because it's in the correlations.
Well, in fact, in this particular example, it's not highly correlated because, so here it says AX is equal to 0. That means that cos iota is equal to 0. So actually, there's not any correlation between the parameters with this particular signal. But I think this is just this is some systematic which we. I mean, it might be a statistical fluctuation. It's probably some systematic error, and we haven't tracked down. But it was close enough that I mean, it doesn't seem like a serious problem, and it went away. So, but it
went away.
I mean, it wasn't seen in simulations. So it's probably some systematic error, maybe in the way the signal was produced, or maybe something in the. I'm not sure exactly what it was. But we never got a real convincing explanation for it. But since it's not completely inconsistent with the data, so we decided that it was okay. So this is an example for pulsar B1937 plus 21 of the B's of K's, so the heterodyned reduced data set. And the black dots are the B's of K's, and the red dots are just the noise level estimated from the B's of K's. So essentially, this is a 1/60th of a hertz bandwidth around the gravitational wave frequency, and this is 1284 for this pulsar. And the data, and we assume with the new student T likelihood that the data is stationary over a 30-minute time scale, and this is over 59 days. You can't tell, but if you zoom in and you look. At 30-minute segments, the data is actually fairly stationary. So we did some further checks with that, with Kolmogorov-Smirnov tests and F tests, and this is another simple way you can check the Gaussianity of the data in the 30-minute segments. So if for each of the for all of the B's of K's, you can calculate the reduced chi-squared for it, and if you do, and then you can calculate the expected variation in the error bars for the reduced chi-squared. And basically, each of these dots represent one of the pulsars. There's 28 of them. And for the majority of the pulsars, the reduced chi-squared was consistent with Gaussian. And for the ones, like there's one here, pulsar number 10, which I think was a pulsar which was near a 60 hertz harmonic. We weren't doing so well with estimating the data, but if you reanalyze the data, throwing away the data which is non-Gaussian, you don't get big changes in the results we get. So for example, for this pulsar, J0030 plus 0451 is the closest pulsar in the data set at 230 parsecs, a frequency of 411 hertz. And we were able to set 95% upper limits of this, and the joint upper limit was 3.8 times 10 to the minus 24, which constrains the ellipticity to 4.8 times 10 to the minus 6. And as you can see, due to the correlation between H naught and cos iota, these tend to peak near 0 here. This is another example. This was the pulsar for which we were able to set the most sensitive upper limit on the ellipticity at 4.5 times 10 to the minus 6. And while this is still above maximum expected ellipticity from theoretical models, there are at least one model, if you consider strange quark stars, solid strange quark stars, that could sustain such strain. So this is a summary of all the 28 pulsars and the upper limits, what we expected to get. This is overlaid over the sensitivity of the interferometers, adjusted by the correct observation times. For the crab in S2, we set an upper limit of 4.1 times 10 to the minus 23, which is only a factor of 30 above the spin-down based upper limit here. And the upper limit we set for the S1 pulsar was about an order of magnitude lower than we did in S1. So to summarize the ellipticity limits we were able to set in S2, for pulsars like the crab, they're not so impressive because they're very low frequencies, so it's just in 10 to the minus 2, 10 to the minus 1 range. So even though we're only a factor of 30 from the spin-down limit, we wouldn't expect the pulsars to be this deformed. But there's at least 4 pulsars which are nearby, which fall into the 10 to the minus 5, 10 to the minus 6 range. Another way to interpret the results is by setting exclusion areas in the moment of inertia ellipticity plane. So when I say we set a spin-down upper limit, we set a limit which was 30 from the spin-down upper limit for the crab. This is assuming a moment of inertia of 10 to the 38 kilograms meter squared for the crab. And there's quite a bit of uncertainty in the moment of inertia of the crab, and also at the distance of the crab, where you can easily get a factor of 50% or a factor of 2 or so in change in the moment of inertia, and that would mean that we're actually closer to the spin-down upper limit than we thought. So another way to interpret the S2 data is you can do some population statistics. So using this sample of pulsars in the galaxy, if you think they're representative to the pulsar population, you can set an upper limit on the average ellipticity of the pulsar population. In this case, the probability of data of a pulsar given a certain ellipticity comes from our upper limits, and then we need to use a prior for the average ellipticity of the pulsar population, which we just used the least informative prior. And when we do this, we can get an upper limit on the average ellipticity of this population, which is about 50% lower than the individual limit on a pulsar. Now, it's like comparing apples and oranges. It's not the same thing, but you get a number which is about 50% lower. And for advanced LIGO, there are more nearby pulsars, so we could set an upper limit on the average strain of the population a few times 10 to the minus 9, which then becomes interesting. So for the S3, S4 analysis, we're currently we've set upper limits on 80 pulsars. There's 150 known pulsars, but many of them we didn't have the timing well enough to include them. We also did some more signal injections, including 2 signals where they were simulating pulsars in binary systems. And we were able to extract them successfully. And this histogram here shows the improvements between the S3 data and the S2 data. The S3 and the S2 upper limits for the 28 pulsars that we used in S2, ranging from a factor of 2 in improvement to 9 or so. But when we add S4 data to that, it adds even more sensitivity, of course. So this is an example of one of the pulsars we injected in S4 at an amplitude of about 3 times 10 to the minus 23. And for most of the pulsars, we were able to extract them quite successfully. This was one of the exceptions. By mistake, the signal we injected in H2 was a factor of 60 smaller than the other interferometer, so that's why you can see that it's peaking pretty close to 0 here. But for L1, even though it's much less sensitive than H1, it still peaks roughly at the right location. So I showed earlier the reduced chi-squared test we did to check the Gaussianity of the B's of K's in S2. Another method we can do this is just by doing Kolmogorov-Smirnov tests. Basically, if you do Kolmogorov-Smirnov tests checking the Gaussianity of segments of 30 minutes, because we only need the data to be stationary for 30 minutes, it can change over longer time scales. Then, and the Kolmogorov-Smirnov test only consists of plotting the cumulative distribution function of a Gaussian distribution and then of what we actually observe. And then you measure the maximum distance between the two distributions. And if we do this with 0.05 significant level, then we see that this is a histogram showing the percent of data rejected for each of the pulsars, and peaks around 5%, which is what we would expect if most of the data is Gaussian. And for the data stretches which are not Gaussian, even if we throw them away, it doesn't affect the results much. So for S3, the geo, it's hard to see here, but the geo above about 1 kilohertz had comparable sensitivity to L1 and other interferometers, so we decided to include it in the analysis. One of the few pulsars above 1 kilohertz is the one we used in S1. So we're able to set an upper limit using all 4 interferometers, and this is the marginalized posterior for the gravitational wave amplitude. It was 5 times 10 to the minus 24, which corresponds to an ellipticity of 4 times 10 to the minus 6 when we include the S4 data. So the best upper limits were for pulsars in the 100 to 200 hertz range, and for the majority of pulsars, we're able to set upper limits less than 10 to the minus 24 with the S3, S4 data. For example, this pulsar 0737 minus 3039, one of the 2 pulsars in this new binary pulsar system that dramatically increased the rates for LIGO in spirals. It's at a distance of 560 parsecs. Frequency of 88 hertz, and we're able to set an upper limit on the gravitational wave amplitude to 5 times 10 to the minus 25 with the spin-down ratio, meaning the ratio between this limit and the one bound by spin-down of 40. But these numbers might change because this is not done using the final calibration of S4, which just came out this Sunday. And also 13 of these pulsars, including one of the ones I'm pointing out here, may have to be excluded from the analysis because of uncertainty in the source parameters. So we get our source parameters, the frequency and the location and so on, from Jodrell Bank, like I said, and they provide us an error estimate for each of the parameters. What they weren't able to provide to us is the covariance error between the correlated errors between the different parameters, and we're not sure right now if one template is sufficient for this particular pulsar, and for in fact 13 of them, so we might have to exclude them. But for about half of the pulsars, we were able to constrain the ellipticity to less than 10 to the minus 5, and for a few of them less than 10 to the minus 6, which starts to become interesting. For the crab pulsar, this is using S4 data, I think. Might be S3. We're getting very close to the spin-down based upper limit. And this is just showing that the 60 hertz harmonic, and although it's close to where we expect the signal for the crab, it's far enough away that using tight filters, we should be able to avoid losing much sensitivity due to this peak. And right now, we're just using data which has a band of a 60th of a hertz around the pulsar frequency, which means that we should not be too affected by the power line.
So on the stochastic search, they sort of knocked out a hertz or two around each power line due to upconversion of correlated noise. And because you're demodulating, I guess you're not sensitive to that.
I think it would still be noise. It could still be elevated noise, but you don't see sidebands on that.
Yeah.
Yeah.
Just maybe because of the fact you're demodulating.
It might be, yeah.
But you also if you're modulating the signal, you're modulating the noise.
Well, we don't, the demodulation doesn't actually take it into the power line. It's not that large of a shift.
Right, but you're within a half a hertz of a power line that has hertz or two sidebands, so I don't know how you're getting out and away from this.
Doesn't look like it. Power line's very narrow.
Power line has 1 or 2 hertz sidebands which are upconverted from low frequency noise.
If you're integrating over a very long period of time, those might disappear when you integrate over a longer time.
And they integrate because you're modulating frequency. Otherwise they wouldn't.
So for S5, we plan to continue with the hardware injections. We've so far injected 10. We're probably going to put 2 more later on in the run. And we'll probably put the injections on and off just to make sure we don't contaminate all the data if anything goes wrong. We might beat the spin-down upper limit for the crab. We plan to expand the list of pulsars we'll look at and provide a monthly status report to the collaboration, and in terms of injections we can show it to everybody to make sure that we don't have any problems. So for example, the crab, this is one of the things we'll be looking at. So this is an example of one of the pulsars we injected into the S5 data just recently using data from between November 23rd to December 6th. So this signal was injected at 9.2 times 10 to the minus 24. So you can see every time I show hardware injections, the amplitude comes down by almost an order of magnitude.
Those are of the whole 2-week period.
Yeah. But actually, just using data for, when you remove data due to the duty cycle or so on, and so on, it's just like 10 days, 5 to 10 days of data. And this is for a pulsar at a frequency of 52.8 hertz, so it's pretty low frequency. And L1, for example, doesn't have great sensitivity at that frequency, so you can see that the posterior is a bit wider. But nonetheless, you can recover the phase from the L1 detector without a problem. And this is just another example, and this pulsar was injected at 4.7 times 10 to the minus 25 into the S5 data. And that's really low strain, and we're still able to easily extract the signal from the data. And this pulsar had a spin down, while the other pulsar, the first one, had a spin down that was low enough to be negligible of the run. And again, the black lines here represent the joint upper limit using data from the 3 interferometers.
These correspond to a signal to noise of what, or compared to that 10 times square root of S over T? I mean, are they 20 times that, or 30, 100?
Depends how you define signal to noise, but
well, if you define it the way I just said, that remember the 10 times square root of S over T?
Right.
What
so
20, 100.
My guess would be around 10.
Right at, and that's
Oh no, 10 above that.
10 above.
10 above the, 10 times the 10.8 limit.
10.8 is not noise variance of 1 whenever it's for a given, for a given false alarm time.
Well, that's what I'm getting at. If you had something like this, this is parameter estimation.
Mm-hmm.
Before parameter estimation is the significance of the signal. There's got to be a number that you can boil it down to. We have a detection, the significance of that.
No. So just to summarize what the other searches have done with, so far they've only analyzed the S2 data except for Einstein at Home, which has looked at S3 data as well. And so for the coherent F statistic search, we've done isolated neutron star search over the whole sky without any spin down parameters, which means that the spin down is limited to the change over 1 over the observation period, and a frequency range from 160 to 228.8 hertz. And your preliminary upper limits in this range range from the best one being 6.6 times 10 to minus 23, and in some regions with spectral contamination up to 10 to the minus 21. And this gives us a range of about 30 parsecs. So basically we're looking for neutron stars in our backyard that somehow we haven't seen yet by other means. And this shows basically the distance versus frequency that we're sensitive to neutron stars. And the red shows the sensitivity of the search, which is for the maximum epsilon given the f dot, the frequency derivative that we're sensitive for in this search. Also, like if there was a epsilon of 10 to the minus 5, and you can't see, but this is about 30 parsecs here. This is about 30 parsecs. And for the CaJAGWR search, we also had to search over orbital parameters. So for this search, there's about 10 to the 12 templates. For this search, 10 to the 10, because it's a smaller frequency band. We did only 6 hours of S2 data because it's so computationally demanding. And the preliminary upper limits for these bands were about 2 times 10 to minus 22, and this corresponds to an ellipticity upper limit of about 5 times 10 to minus 24 for CaJAGWR. And then the only result we have so far for the incoherent searches is from the Huff transform. We did an all-sky search, one spin down between 200 and 400 hertz using the full S2 data set. This is and the upper limits were from the best one being 4.4 times 10 to the minus 23 up to about 10 to the minus 21. And this is about a factor of an order of magnitude larger than the best upper limits we can get with the known pulsar search, and that's because that the parameter space is much larger in this case. So the detection threshold basically has to be set higher. For Einstein at home, it's a publicly distributed computing project to look for isolated pulsars using LIGO geodata. Makes use of the F-statistic method. Currently, there's 142,000 users, 240,000 computers from 167 countries, delivering about 70 teraflops of computing power 24/7. So this will be the computational workhorse for future pulsar searches, and a lot of our effort will be oriented around Einstein at home in the future. The S3 results show no evidence for strong pulsar signals, and the outliers are consistent with numerical artifact. So these plots here show the value of twice the F statistic over declination and right ascension with injections and without injections. The line here are due to spectral lines. So basically what happens is because you demodulate data, most of the for a lot of the sky, the spectral lines are washed away, but there's a certain arc in the sky where the demodulation of the data is not great, and that's where we get most of the contamination from the spectral lines. So in this case, these are the pulsar injections. And if you go to the Einstein at Home webpage, you can find a report on these S3 results. And in the future, we plan to expand the list of pulsar for the time domain search, continue with Einstein at Home work. We plan to expand the search look for signals, again, for CaJAGWR and also other LMXBs. And for the incoherent searches, we're going to do an all-sky wideband search for isolated pulsars. And the goal is to connect the coherent searches and the incoherent searches to develop a hierarchical method, which is the best way that we can, which is the way we can get the most sensitivity given the limited computational resources. And that's all I had to say, so thank you.
Will be easier because we know everything.